Okay, hi again, everyone. So in this video, let's go ahead and practice drawing resonance structures. Before we practice drawing any kind of structure, resonance structure, or just any um, molecular formula that's given to you, and you have to draw out what the structure actually looks like, let's go over two quick rules that we should follow. One rule that we'll always follow is the octet rule. And I know you know what this is. The octet rule simply states that the amount of electrons that our atoms have that they bring to the molecule and the electrons that they receive from the atom that they're bonded to, that is to say that they're sharing, all have to add up to 8. And this rule is absolutely true for the elements carbon, nitrogen, oxygen, and fluorine. So if you have a periodic table, you should get it out right now. Just like print it out, pause this video, and just get a periodic table in front of you. So you'll be able to basically see what I'm referencing. So CNOF, carbon, nitrogen, oxygen, and fluorine, are on the top right-hand side of your periodic table in the P block elements. And these atoms, whenever they're found in any kind of chemical structure, always follow the octet rule. The second rule that we should follow is the formal charge of each atom. Now, there's an easy way of calculating formal charge, which we'll see as we draw out our structures, and there's a more like a systematic equation that we can use. And the systematic equation is this. You take the valence of the neutral atom and we'll see what all of this means, minus the sum of the number of electrons. Let's just say, yeah, total number of electrons in lone pairs plus the number of bonds. So we'll see what all of this means, but a really easy way of remembering this equation is to just say that this is the number of dots and this is the number of lines. There's a third rule that's not always followed, but I'll just put it in here so you know what it is. And I think your book calls this the common valency, if I remember correctly. The common valency rule, or I just call it the bonding pattern. The bonding pattern rule. So this is a good guide that you can follow to figure out how many bonds your atoms should have. So if you have hydrogen or a halogen, which we'll say is symbolized by an X. X usually means halogen. So that's all the way on the right side of your periodic table. So that is FClBri. Fluorine down to iodine. That's X, okay? So if you have hydrogen or a halogen, it's going to be monovalent. which means it only wants to bond with one other atom. If you have oxygen or silicon, and you know what? We're never going to have silicon, or I'm sorry, that's sulfur. So I'm just going to say oxygen. That's going to be divalent. So oxygens want to be bonded to two other atoms or to just one other atom in a double bond. If we have a nitrogen or a phosphorus, they like to be trivalent. And as you already know, carbons are tetravalent. So what does all this mean? It basically just means, for example, if you have an oxygen atom in your chemical structure, it's divalent, right? So it's going to want to be bonded to two other atoms, or it can be bonded to just one other atom, but it'll be double bonded. So like, let's say to a carbon, for example, that's divalent. Nitrogen and phosphorus, and really just the nitrogen, we're not likely to see phosphorus too much. Nitrogen wants to be trivalent, so usually it'll try to be bonded to three other things, like let's say hydrogens, and then it'll have that lone pair, because if you look at your periodic table, you'll see that it's a group 5 element, and group 5 elements have 5 electrons in their valence shell. So you have to account for that. So here's 1 electron in its valence, here's 2, here's 3, here's 4, there's 5. So it does have a lone pair, but it bonded to 3 things, 1, 2, and 3. So that's trivalent. Another pattern nitrogen can follow is to maybe be double bonded to something and single bonded to something else. So like a carbon on this side and a carbon on that side. So either way, that's still trivalent. Here's 1 bond, 2 bonds, and 3 bonds. And carbon is tetravalent. So we all know that. That can be something as simple as, let's say, methane. There's 4 bonds. Or it could be something a little bit more fancier. Like let's say it's double bonded to an oxygen. Then it has a hydrogen also bonded to it. And then it's bonded to another like chain, like a hydrocarbon chain. So there's 1 bond of the carbon, there's 2, there's 3, and there's 4. Tetravalent. 1, 2, 3, 4. So those are the 3 general rules that we follow whenever we're trying to build a structure if all we're given is its molecular formula or a kind of incomplete diagram. So let's put these rules to work and let's start creating some structures. So the first one, let's see. The first one I'll show you is one that you've already seen before. It was in your in-class problems. So let's say we have NO2 minus, okay? NO2 minus. So whatever letter is, oops, just erase the whole thing. So whatever letter is written on the left side is usually the atom that's going to be in the center of our structure. So here N is on the left side, right? So N's probably going to be in the middle, and it's going to have 2 oxygens sticking out on the side of it. So let's say we want to follow our first rule, which is the octet rule for nitrogen. Well, it's got 1 atom, 1 electron here, 2, 3, 4. So we still want to get to 8 because remember, for the octet rule for our CNOFs, we always, always, always follow it. We never violate that rule. For other atoms in the periodic table, you can kind of violate it. You can expand the octet. But for carbon, nitrogen, oxygen, fluorine, you never not have 8 electrons around those atoms. So that's just, that's a rule that never gets broken. So around our central nitrogen atom here, we have 4 electrons so far. It's bringing 2 to the table. So maybe we can double bond one of our oxygens. So let's say we allow for that to happen. And we can't forget about its lone pairs that it has, right? It's group 5. So here's the valence electrons that this nitrogen has. 1, 2, 3, 4, 5. And let's count up how many total number of electrons that it has and that it's sharing. Well, right here, there's 2, there's 4, there's 6, and there's 8, right? That's a single bond. I know I drew it pretty thick, but there's your single bond. So the octet rule for the central nitrogen is fulfilled. So far, so good. Let's fill out the oxygens on either side. So on the left oxygen, we know we must have a lone pair of electrons here and here, because we know oxygen is group 6 on our periodic table. It has 6 electrons in its valence shell. And sure enough, we drew 6 in. Here's 1, 2, 3, 4, 5, and 6. Are we fulfilling the octet rule for oxygen? I think we are, because here's 2 for our oxygen, right? There's 2 more, so that's 4. There's 6 that it has in its vicinity, and there's 8. Sweet. So the left-sided oxygen fulfills its octet rule. What about the right side? Well, if we fill in its lone pairs, except the one on the right is going to have 3 lone pairs, probably. Let's see if that hunch is right. Then we're going to fulfill its octet rule, because the amount of, dang it, electrons around it are 2 right there, 4, 6, 8. So the octet rule for all 3 of our atoms has been fulfilled. So we're in good shape. So the only other rule really that we have to follow, remember I said the bonding pattern you can kind of skip, rule number 3, just make sure your formal charges like add up properly. Like when you add things up, they have to add up properly. 2 plus 2 equals 4. You can't say 2 plus 2 equals 5. That's never a thing. So let's add up our formal charges here. And we're not even going to use that equation that I showed you. Let me rewrite this so it's a little bit easier to see, okay? So here's what our structure looks like so far that we're building from scratch. So now we're going to put formal charges on it. The nitrogen, here's the easy way of doing it. You know nitrogen is a group 5 element, and its valence shell therefore has 5 electrons. What does this nitrogen have? 1 electron, 2, 3, 4, 5. So its formal charge is 0. We didn't add any electrons, we didn't subtract any. What about the left-sided oxygen? Group 6 element, its valence shell has 6 electrons. How many electrons in the valence shell of our left oxygen? I count 1, 2, 3, 4, 5, 6. So this oxygen has a formal charge of 0. What about the one on the right? 1, 2, 3, 4, 5, 6, 7. That's one too many electrons in its valence shell. One too many. So it must have a formal charge of -1. What's 0 plus 0 plus -1? -1. So our formal charges work out. Here's the long way of doing it, if you're really anal retentive. So we'll use our formula. So for our left-sided oxygen, its valence when it's neutral is 6, right? And then we subtract the amount of free dots that we see. I see 1, 2, 3, 4. There's 2 lone pairs, so there's 4 dots. So we just add up the dots with the lines. How many lines? 1 line and 2 lines. 4 plus 2 is 6. 6 minus 6 is 0. It should be 0, and we said it was 0. What about this nitrogen? What is its valence number when it's a neutral atom? 5, because it's a group 5 atom. Minus how many dots around it? 1, 2, so there's 2. How many lines around it? 1, 2, 3. 2 plus 3 is 5. 5 minus 5 is 5. Its formal charge had better have been 0, and it was. And how about our last element, the oxygen on the right side? Valence when it's neutral is 6, minus how many dots around it? 6. How many lines around it? 1. 6 plus 1 is 7. 6 minus 7 is -1. Yep, it was -1. So you can use this formula, or you can literally just count the stuff around the atom. So I would just say count. It's just so much simpler. But we went through this very systematically, and we discovered that the way we drew our structure was correct. We fulfilled the octet rule. There's only 2 rules we have to fulfill: the octet rule and the formal charge rule. And everything worked out. So the structure that we built, let me redraw it again. Is the correct structure. Now, if in your test or quiz you're asked to draw out the resonance structures of whatever compound is given to you, and then you go ahead and do that, and the easiest way to draw out resonance structures is to simply push electrons, okay? Whoops. You're pushing electrons from where they're found, away to somewhere else. So let me redraw this again. So this was our guy, right? And he had a lot of electrons on this oxygen, which is why it had a negative charge. The oxygen on the right side had only 2 lone pairs. That's what we looked like, right? So I'm seeing a negative charge on the right side, a lot of electron density. So what I want to do is move it away to its neighbor. So you never do something crazy like this. You never like take these electrons on the right side and jump an atom. That's stupid. You can only go one thing over. So you can only move these electrons to that bond right there, or even maybe to this atom, but we'll just say to that neighboring bond. We'll keep it textbook. So when that happens, we're overburdening our nitrogen, aren't we? Because our nitrogen, what we ended up doing was creating this structure. and we expanded our nitrogen's octet. And we can't expand the octet for CNOF. It can only be 8. Can't be more than 8 or less than 8. So if we're moving electrons from the oxygen on the right side to next to the nitrogen, then we want to be moving this electron density over here onto that oxygen, so the nitrogen is not overburdened with too many electrons, forcing it to expand its octet. When we do that, we end up creating our resonance structure that looks like this. Because these two electrons right here got moved to here, right? So here they are. So now we're bonded, and let's say these two electrons were blue, and we moved them over 1. So there they are. And now our negative charge is on the left oxygen. So there's our two, and we can't draw like a third resonance structure. We're out of atoms. There's nothing else to do. So these are our two resonance structures. And when we've drawn them out, you just put brackets around everything. Okay? So let's do another problem. And this time we'll go a little bit faster. Let's see, I'll give you a different one. What if I gave you, and this one is, it looks hard. What if I gave you CH3, CO, NH2? So don't worry, this looks hard, but we'll go through it. It actually isn't. So I know I told you that everything on the left side is probably in the center, but in this case, we're kind of breaking that rule of thumb. And let's say that this carbon right here is the one that's in the center. Okay? So that carbon is hooked up to an oxygen, that one right there. It's hooked up to this methyl group. So let's say like that. And it's probably hooked up to that nitrogen. So let's say like that. I mean, that's a pretty good guess to start out with. And now we follow our two rules. Octet rule, and then we do our charges. Everything's got to add up properly. Octet and charge. That's it. So does our central carbon follow the octet rule? No, it does not. Here's 2 electrons right there, right? That's 2. Here's 2 more right there. That's 4. There's 2 more right there. That's 6. But carbon is one of our CNOFs. 6 is not good enough. 6 does not equal 8. Only 8 equals 8. So maybe this was a double bond. We're just kind of playing with the structure to get what we want. If that was a double bond, then the octet rule for the carbon is fulfilled. Now let's draw in some of the extra electrons. This NH2 right here, let me expand that out a little bit more so it's clearer. There's 1 hydrogen and there's another hydrogen on that nitrogen, right? But nitrogen is a group 5 element. So here's one of its valence electrons, here's another one, and here's a third one. So it must have a lone pair that are not bonded to anything. The oxygen obviously has two lone pairs because it's a group 6 atom, right? Check on your periodic table. So there's its 6 electrons. 1, 2, 3, 4, 5, 6. And the methyl is obviously, that looks fine. The CH3 on the left side, that looks just fine. So we've accounted for all of our substances, all of our atoms or elements. We had an H3 and an H2. So we had 5 H's total, and we do. There's 3 H's, and here's 2 H's. We had a couple of carbons. There's 1 carbon and 2 carbon, or here, 1 carbon and 2 carbon. So there's 1 carbon and another carbon. And then we had an oxygen, which is right here. So in terms of just like bean counting all of our atoms, everything has been accounted for. We followed our octet rule for our carbons and nitrogens and oxygens. So we're good in that category. Now all we have to do is make sure that our formal charge is okay, because let me rewrite this. This has gotten really messy again. Because the structure that I had given you was CH3, CO, and H2, right? But I didn't say that it was plus or minus. I didn't say anything like that. It was just neutral. So the structure that we derived, I'm going to redraw it. Better have had no total charge on it. So let's go ahead and look at the formal charges on all of our atoms. The methyl group on the right side, that is fine. There's nothing wrong with that. That's just a CH3 sticking off of a carbon. So no need to examine that anymore. What about the central carbon? Well, carbon has a valency of 4. It's a group 4 element. Look on your periodic table. So it has 4 electrons in its valence shell. Does it have 4 here? Yes, it does. 1, 2, 3, 4. So it doesn't have any more or less electrons than it should have. It has the right amount. So that central carbon has no charge. It's 0. What about our oxygen? It's a group 6, so its valence shell has 6 electrons, and here we have 6 electrons. There's 1, 2, 3, 4, 5, 6. So that oxygen has a charge of 0. What about our nitrogen? It's a group 5 element, so its valence shell has 5 electrons. Do we have 5 here? Yes, we do. This nitrogen has 1 electron there, 2, 3, and then remember our 2 H's that are bonded to it. So like there's 1, well, there's 1 and there's 1. So 4, 5. So this nitrogen has a charge of 0. So this molecule that we drew has no charge, which is good because we were given a molecule that had no charge. But what if you were told to draw resonance structures, or in this case, resonance structure, just one? So let me redraw this. Well, the way we draw resonance structures is simply by pushing electrons from where there's a lot of them to where there's not. And we don't jump atoms. We go step by step. We go from neighbor to neighbor. So the way you do that here, and I'll do it in pink, So the way you do that here would be to say, I'm seeing a lot of electron density in that carbonyl area, the C double bonded to an O. So let me go ahead and move some of that out of the way. Actually, let me just, yeah, let's do that. So we'll move some of these electrons out of the way and we'll put them onto that oxygen. And remember, we talked about electronegativity. We talked about electronegativity. And the further up and to the right you go on the periodic table, the more electronegative you are. Well, oxygen is pretty far up there. So it has no problems stealing somebody else's electrons. It actually kind of wants to be negative. So if that's what happens, then that frees up the carbon in the middle. This carbon in the middle now has lost a few electrons from around of itself, from around itself. So it can suck up these electrons of the nitrogen, and so we can put them here. So you see how we're just like following where the electrons are going, like follow the leader. We didn't skip over anything. We just move them from neighbor to neighbor. So when we do that, we end up creating this structure. So that looks a little weird. All of the atoms are taken account of. But let's go ahead and look at the formal charges. The formal charge around our central carbon is still 4. Well, I'm sorry, it's still 0 because it's bonded to 4 things. So this carbon has a charge of 0. But what about the oxygen? Well, it has 1, 2, 3, 4, 5, 6, and 7 electrons in its valence shell. It's only supposed to have 6. So you know that oxygen is -1. What about nitrogen? Here, let me show you. So the extra electrons that we put on, I'll put them in pink. They were these right here, right? And let's make these green. And so that green is right here. So what about our nitrogen? Well, our nitrogen has how many electrons in its valence shell now? 1 right there, 2 right there, and it has 2 hydrogens bonded to it. So that's 3, 4. And it doesn't have that lone pair anymore. So it only has 4 electrons in its valence shell. It's supposed to have 5 because it's a group 5 element. So it is +1. And you can go through the formal calculation. You can use that equation. The valency when you're neutral minus the number of dots plus lines. But we won't even do that because we counted it right the way we did. So in this structure on the right, we have a -1 and a +1. They're going to cancel each other out to have a formal charge of 0, which is what we expected to have because we never had a charge given to us in the first place. So that resonance structure checks out. Okay, let's do 2 more. Let's do, what should we do? Let's do HCO2 negative. So let's draw that. So C is probably going to be in the middle, and it has two oxygens and a hydrogen sticking off of it. So it might look something like this. But that looks a little strange if you ask me. Here, let me. So it might look something like this. But as we said, that looks a little weird. Carbon has it's our one of our CNOF octet atoms, and in this case we have 2, 4, and 6. So probably this carbon is double bonded to one of the oxygens, like that. And let's say we fulfill the octet rule for that oxygen on the right by drawing in those electrons, and the one on the top by drawing in ugh, by drawing in 2 lone pairs there. And even though this looks a little strange, I think it might work. Um, we fulfilled the octet rule for the carbon. We have fulfilled the octet rule for both oxygens, right? 2, 4, 6, and 8. And the oxygen on the top has 2, 4, 5, 6, 7, 8 total electrons that it's sharing. So yes, octet rule satisfied for both oxygens and the carbon. How about formal charges? Well, the carbon, I hope you know by now, is just neutral because it has, I'm going to redraw this again. Okay, better already. So I hope you know that the carbon in the middle is neutral. It's a group 4 element, and its valence has only 4 electrons. There's 1, there's 2, there's 3, there's 4. No more, no less. So that carbon is 0 charge. That's good. What about the oxygen at the top? 1, 2, 3, 4, 5, 6. It's a group 6 element. So that's 0. What about the oxygen on the right? 2, 4, 6, 7. It has 7 electrons in its valence shell. So that is a -1. So this molecule overall has a -1 charge. And that's what we said it needed to have. Right? -1. So the way we drew it was accurate. And now what if the exam or quiz you're taking says draw resonance structures, if any? Well, we just push stuff around. We push the electrons around from where they are to where they are not. So how do you want to do this? Well, that oxygen already has a negative charge on it. So let's unburden that oxygen by moving these electrons over there. But now we've overburdened our central carbon by putting too many electrons around it. So let's unburden it by moving those electrons over there. It really is just that simple. So now we've made something like this. And there's our resonance structure. So I was going to do one more, but let's stop here because I think we got to move on to the next topic. And if in this playlist I decide I have a little bit more time, maybe I'll throw in one or two more resonance structures then. But for right now, let's go ahead and pause.